In our last video, we began the conversation about heat, which is the transfer of thermal energy. This transfer can happen from the system to the environment, from the environment back into the system, or it can happen within the system itself. And that's going to lead us to our topic today when thermal energy is transferred within the system itself. And the opportunity to do that gives us a way of finding the specific heat capacity of an object through a process called calorimetry. Calorimetry uses the transfer of thermal energy within a system to identify the specific heat capacity of an unknown substance, or the unknown specific heat capacity of a substance. I've drawn a calorimeter for you here. I'd like you to draw one into your notes as well. I've labeled the parts. Outside the calorimeter is an insulated container. That insulation is very, very important. It keeps the transfer of thermal energy within the system. So I want there not to be an opportunity for the heat to go in or the heat to leave the system. So it's got to be insulated. So you might have some insulated substance on the outside, and this might be a vacuum on the inside that keeps heat from flowing, keeps thermal energy from flowing in or out. The container itself, though, needs to be a metal can. That's really actually very important because I want this process to happen kind of quickly. And I want it to be a metal that I actually already know the specific heat capacity of it. I'm going to put the block of my unknown specific heat capacity into water, and I'm going to measure the temperature changes that are going on with that looks like a worm, but it's actually a thermometer for you to be able to identify the specific heat capacity or the temperature changes that are going on. All right, so there are some conditions that need to be followed and understood at the very beginning in this process. First of all, before I put my block into the water and the metal can, I have to bring the water and the can to the same temperature. And I have to measure what that is. I have to record what that temperature is. Then what I'm going to do is insert the block which has a distinctly different temperature. So one is not going to be at 35 degrees Celsius, the water in the metal can at 35 degrees Celsius, and the block at 32 degrees Celsius. That would be too difficult to try to work through. So it has to be a very distinctly different temperature. Then you're going to allow equilibrium to happen, and at equilibrium they will all achieve the same temperature. Now here's the equation that we're working off of. So I'm going to have a temperature change and therefore a heat exchange in the water, in the metal can, and in the block with the unknown C. I am specifically looking for this piece of my block, which means I better know everything else. So I have to have found my masses first. That's a given that I've already done that. I'm going to record my change in temperature. I'll know the specific heat capacity of the water, and I'll know the specific heat capacity of my metal can. So my C should be the only thing I don't know, but I've got all these Q's hanging out here. How am I going to manage this if I don't know my individual Q's? Here's the trick to this. If this is a closed system, all of my changes in heat add up to 0. Because say the water and the metal can are at a higher temperature and the block is at a distinctly lower temperature, then what the water and the metal can, because the hotter objects will flow their thermal energy to the colder objects, what the water and the metal can lose in heat, it's going to be gained by my block. So the net change is going to be equal to 0. Think of it this way. You have $20 in your pocket and your buddy has $10 in his pocket, and you're feeling in a very generous mood that day. So between the two of you, you have $30, but you're going to give him 5 of your dollars. That means now you have 15, and because you've given him 5, he has 15. But there's no net change in the amount that you have at the end. You both have 30. It's exactly the same thing that's happening within my calorimeter. What somebody else loses, somebody else gains, so there's no net change in the total heat of the system. That's my letter D contingency, or that's my letter D necessary condition. Net change in Q is 0. That is absolutely essential. And by the way, that can only happen when I have an insulated container. And we'll talk about that again in a little bit. So the heat transfer of the process looks like this. The Q of the can plus the Q of the water plus the Q of the block is equal to, net change is 0. When I add them all up, it's going to equal 0. Now I don't need to know my individual Q's. I just need to know my expressions, which will add up to 0. So it's going to look like this. In longhand form, it's going to be the mass of the can, and I'm just going to write the first one because it gets to be a little redundant, times C of the can, times the delta T of the can, plus ... So I'm just doing the MC delta T expression for all of these. Now, if the whole thing adds up to 0, it is axiomatic that at least one of them is negative. Therefore, at least one is negative. So in this case, I have a transfer of thermal energy. I have heat occurring within the system, but not leaking out to or being or having thermal energy brought in from the environment. The environment is not a part of this process at all. And when this is the case, when everything happens within the system, the process is said to be adiabatic. It's adiabatic because thermal energy does not exit or enter the system. That is the definition of adiabatic. All of the thermal energy is maintained within the system. It may transfer from one piece of the system to the next, but the net change in heat is 0. So example of that would be a thermos. So you put your coffee in the thermos, and your coffee's too hot, and your thermos is very well insulated, so you want to cool your coffee down. So you drop an ice cube in, and then you close it up tight. All of the heat exchanges are going to happen within the system of the coffee and the ice, not with the thermos itself. That is an adiabatic system. All right, so let me do an example of this so you can see the math involved. An insulated aluminum can whose mass is 0.2 kilograms contains 0.3 kilograms of water at 25 degrees Celsius. A 0.1 kilogram metal block whose temperature is 80 degrees Celsius is lowered into the temperature. The final temperature of the system is 30 degrees Celsius. There should be a period there. Sorry, find the specific heat capacity of the block. So this is truly a calorimeter that I'm working with. I am looking for the specific heat capacity of the block. So I have 3 things that are happening. I've got my can, I've got my water, and I've got my metal block. And so I'm going to write my knowns and my unknowns of all 3 of those on the side. So for my can, my mass is 0.2 kilograms. The specific heat capacity of the can, because it's aluminum, is 900 joules per kilogram degrees Celsius, And the delta T of the can started out at 25 degrees Celsius and it ends up at 30 degrees Celsius. So it's T minus T naught. So it's 30 minus 20, which is going to give me a positive 10 degrees Celsius. I'm not looking at the right numbers. I'm sorry. I have really got the wrong numbers here, so let me backtrack. My initial temperature of the water is 25 degrees Celsius, and the final temperature of the water is 30 degrees Celsius. So it is 30 minus 25, which gives me a 5 degrees Celsius delta T. All right, so now let's talk about the water. The mass of the water is 0.3 kilograms. The specific heat capacity of the water is 4,180 joules per kilogram degrees Celsius. And the delta T of the water is going to be the same as the delta T of the can because they were at equilibrium to start with. So my delta T is again 30 minus 25, which is 5 degrees Celsius. And then finally, my block. The mass of the block is 0.1 kilogram. The C of the block is what I don't know. The delta T of the block, and this is kind of important, you should be anticipating something here better be negative, because if my total change in heat is 0, I've got some positive stuff going on here, so I need to have a negative thing going on here, and it's actually quite negative. My final temperature is 30, but my initial temperature was 80, so my final change is going to be a negative 50 degrees Celsius. All right, so you can do this individually or you can do it all as one. I really don't care how you do it. I'm going to put it all in one equation, but I'm going to look for them individually. I'm going to work with them individually within the big equation. Your parentheses key is your friend. Your parentheses button is your friend in these problems. All right, so let's go ahead and set up first my Q equation. This is going to end up being, my block is going to be negative because it's the only thing that has a negative piece of data in it. So the Q of the can plus the Q of the water minus the Q of the block is equal to 0. Or another way of saying it is Q of the can plus Q of the water is equal to Q of the block. I'm just using abbreviations there. Hope you can get that. Now I'm just going to write the numbers in. So my Q of the can is going to be 0.2. This is my MC delta T. So my M is 0.2 times 900 times 5 plus 0.3 times 4,180 times 5 is equal to, now the block was negative over here, and perhaps I shouldn't have made this jump. I don't like working with negative numbers. My block was negative over here. I made it positive by moving it over, which means my negative on the left becomes a positive on the right. So my number is going to be 0.1 times C, which I don't know, times a negative 50. And I like having this one over here too because now, I'm sorry, I did that. It's a positive 50. I like having my C over here because I've got C already kind of all alone. So filling all of this out, on this side of the equation, when I add these two up, I get 7,170 joules is equal to 50 times 0.1 is 5. C. My C is right here. So these two together is 5, and then C. C then is equal to 1,434 joules per kilogram degree Celsius. And I would normally take you through all of what's happening with the units for this. It all works out actually kind of perfectly, but I am not going to take the time to do that. That's something that you can do on your own, how this works out to be joules per kilogram degree Celsius. But I know it has to be because everything is in joules, everything is in kilograms, everything is in degrees Celsius, so my C is going to have to work out as joules per kilogram degree Celsius. As long as all my units are correct, I know it's going to turn out that way accurately. All right, now the next problem, it takes a different take on this. It's still a calorimeter, but it's a calorimeter that is going to look for a different way of finding the specific heat capacity. Instead, it does it using basal metabolic rate of the rabbit. So what I'm going to do is give you the formula for that to start with. Basal metabolic rate is equal to the heat of the air all over the change in temperature. So let's write down what we know and what we don't know. I do know that the heat of the air is going to be MC delta T. So it's 2 times 10 to the mass is -3. MC for air is about 1,000. Delta T is going to be 2.7 degrees Celsius all over the change in temperature, which is I'm sorry, my delta T is delta time. Can I backtrack here? This is rate. I'm thinking ahead, and I should not have been doing that. I should have been concentrating on what I was doing. So let's backtrack here. Basal metabolic rate. So I want to know how much heat is being transferred into the air per second. That's going to tell me the basal metabolic rate of the animal, in this case a rabbit, by the fact that it is increasing the temperature of the air. So I'm first going to find out how much is the air being increased and by what rate is it being increased. In other words, I'm going to divide it by the time, and it actually tells you that it is each second. So my delta T is 1 second. I apologize for that. The first one, it's not temperature, it's time. So the top is MC delta T. The bottom is my time. Not my temperature, is my time, which is 1 second. So what you end up having is 50 or 5.4 joules all over 1 second. A joule per second is a watt, so you end up with 5.4 watts. All right, so this would be the equation for basal metabolic rate, which kind of gives you the same idea of what's happening. How capable is the rabbit of increasing the temperature of the air? All right, and it's its own kind of built-in calorimeter or a closed environment where you're able to do that. I am going to, first of all, tell you that the homework for tonight is 21 through 25. And then I'm going to just introduce this next section on phase changes. You had this in chemistry, so I know this is not new information for you, so I'm not going to spend a lot of time on it, but I do need you to know the warming graph of water and what all that means. I don't know why my I don't know why my lines are so far off. It's kind of weird. All right, melting and freezing. Do you remember what the graph looks like for melting and freezing of water? It isn't just a straight linear graph of as I add heat, I get a corresponding bump in temperature. I can continually be adding heat to my system, but sometimes I don't get a rise in temperature if my system is going through a phase change. So this is what it's going to look like. When heat is added or removed from an object, the first thing you think of is a change in temperature. You automatically think if I heat an object up, it's going to get hotter, and generally speaking, it does. But there can also be a change in phase. And that requires heat for that to happen. And when it is changing phase, it is not changing temperature. Let me say that again. When it is changing phase, all of the heat that I'm pumping into this system is now going into breaking those intermolecular bonds that will allow for a phase change. So the intermolecular bonds that make it a solid have to be torn apart, and that takes energy before it can then start putting that thermal energy into increased kinetic energy of the molecules. So the graph of the heating of water is going to look like this. You've seen this before. It's not anything new. And I'm going to pull this back just so that you can see the whole thing. Are we able to see? Pretty much we can see the whole thing right here. So it's going to look like this. I'm going to start down here and rise it up to my my melting or freezing point, and this is water. So this point, I'm at the temperature of 0 degrees Celsius. And at this point, when I'm adding heat, that's Q down here, as I'm adding heat to my system, I am raising the temperature of my system. That kind of makes sense. That's what you expect to have happening. But when I hit 0 degrees, which is my melting / freezing point, now I'm going to hit a plateau. I'm still adding energy, but notice I'm not getting a corresponding bump in my temperature. So it's going to keep melting, keep melting until I get to this point where everything now has melted. Now my heat does not need to go into breaking intermolecular bonds. Now my heat can do the entire job of simply raising the temperature of my water. So now I'm going to get a bump in temperature as I go up until I hit this point. And at this point, now I've hit 100 degrees. And at 100 degrees, I'm ready for, and this is Celsius, I'm ready for another phase change. So I've gone from all solid down here, and all I'm doing is raising the temperature of a solid. And by the way, by raising the temperature of a material, that's called sensible heat. So at this point, I'm at all solid. And if I'm moving in the positive direction on my x-axis, then I am melting my solid. So that's what's happening at the plateau. And at the end of the plateau, I've gone from all solid at the beginning to all liquid at the end. It's a little of both as I go through, some solid, some liquid, and more solid at the beginning, more liquid at the end, until at the very end, it's all liquid. So once I've hit all liquid, now I'm ready to bump my temperature up. And at this point now, I am raising the temperature of my liquid. And again, this is going to be called sensible heat. Once I get to 100 degrees now, I'm at the moment when I first hit 100 degrees, I am all liquid. But as I go through the phase change, I turn from all liquid to the very end of it where I'm all gas. And that process, when it's a rapid phase change at one temperature, is called boiling. A phase change from liquid to gas can be called boiling or it can be evaporation. Lumped together, the phase change in general is called vaporization. But when it's a rapid phase change at a specific temperature, then it's boiling. So that's legitimate to call it boiling. If I'm going in the opposite direction, it's going to be condensation, but we've established that I'm moving in the positive X direction, so it's only boiling in this case. And then when I'm all done turning it to gas, if I still have the gas, it's not just gone into the environment, then I can raise the temperature of the gas. So again, at this point, if I'm raising the temperature, what kind of heat is that called? It is, again, sensible heat. And there's a reason that I'm giving you that name over and over and over again of sensible heat. Sensible heat is going to use the formula Q is equal to mc delta T. Every time it's going to use the formula Q is equal to mc delta T. And for this, always sensible heat, Q is equal to mc delta T, because what is the end result of my adding heat to the system? I'm not changing the mass, I'm not changing the specific heat capacity, I'm raising the temperature. So sensible heat is about raising the temperature. That's why I'm using the Q is equal to mc delta T equation. And in this case, C for ice is not 4,180, but it's 2090 joules per kilogram degree Celsius. Now for raising the temperature of liquid, again, because it's sensible heat, I'm using Q is equal to mc delta T, and you already know that the specific heat capacity for water is 4,180, where C is liquid water, so I'm just going to call it water. Is 4,180. Again, it's joules per kilogram degree Celsius. Up here, I've got Q is equal to mc delta T again, but C of my steam, or my gas, is going to be 1,975 joules per kilogram degree Celsius. I'm sorry, 1,970 joules per kilogram degree Celsius. And I'm putting them here on the graph, even though they're on your paper. I would really encourage you to, as you're working through phase changes, I would encourage you to actually walk your finger through the parts of the graph where you are and saying, where am I? If I'm here, if I'm at the very beginning, then I have to go through this phase change. That's its own equation. Then I have to go through raising my temperature. That's its own equation with its own constants. I go through boiling, and let's say that I'm raising it up to here. As I walk through the graph, I'm going to be keeping track of what equation I need, and I'm also going to be keeping track of what constants I need. So this graph is your friend. The melting is, these are called latent heats, and I actually need to mark this down here. This little packet of heat that is necessary to melt my substance is called the latent heat of fusion. Latent heat is any heat that is a phase change, and any heat that is a temperature change is a sensible heat. Latent heat causes phase change. So this is the latent heat of fusion, where all of my Q goes into breaking bonds, the intermolecular bonds that hold them in place as a solid. So, and this is why, because it's breaking the bonds, it's why you're not getting a bump in temperature. That latent heat is being used for one specific purpose. So you're not getting a rise in temperature. And by the way, the heat of fusion is given the symbol L sub F, latent heat of fusion. And the formula for this, and we'll get into that later, you've not seen it yet, is Q is equal to M L sub F, where the latent heat of fusion is a constant for that specific material. And again, that's going to be on your charts, and we'll talk about those when we start doing some actual problems with it. I'll tell you now, there's not a reason not to. The latent heat of water is, the latent heat of fusion for water is 3.35 times 10 to the 5th joules per kilogram. We'll get into that when we actually start talking about this down here. And then this one is going to be, this packet is going to be called the heat of vaporization. And it's the exact same thing, only I'm not breaking the bonds from solid to liquid. I'm breaking the bonds of liquid to a gas. So the heat of vaporization is where the Q goes into breaking the intermolecular bonds of a solid to a gas. I'm sorry, from a liquid to a gas. I think I'm just going to stop here. I don't think there's anything more that I need to say from this graph. I will call this Q is equal to mL sub V. Heat of vaporization is L sub V, and that's a constant, and it's 2.25 times 10 to the 6th, I believe, joules per kilogram. What do you notice is missing from this equation? You're used to the MC delta T, MC delta T, MC delta T. Why isn't it ML sub F delta T? Notice what I'm not doing here with my heat of fusion. I am not changing the temperature. I'm only changing or I'm only breaking the bond. So there's no delta T in that equation, and understandably so. Now let's talk about this heat of fusion. What does this actually mean, the heat of fusion? How are we going to define this? Heat of fusion, L sub F, of a solid, because heat of fusion is where you go to or from a solid and a liquid, is defined. So the heat of fusion is the energy needed to melt 1 kilogram. For what we do, it's always 1 kilogram of a substance into liquid at the melting point. So I'm not playing with pressure with this at all. We're making it the melting point that would be true at, I think it's like 25 degrees Celsius. Or I'm sorry, no, I'm not saying that right. I'm sorry. It's going to be the melting point that would be true at 1 atmosphere, which really doesn't influence the melting point as much as it does the boiling point. So we're not changing the melting points or the boiling points because of pressure. It's the standard melting point, 0 degrees for water. And for water, L sub F is equal to 3.35 times 10 to the 5th joules per kilogram. Not kilogram degrees Celsius, just joules per kilogram, because I don't have a change in temperature going on. And again, I want you to note there is no increase in temperature as I add heat at this point in my system. And this, by the way, works when you have, the graph is going to look like this. It's going to be true when you have a melting point, not a melting zone. So I need to have pretty sharp and distinct plateaus in my graph. It can't be something like this. This would be an amorphous solid, would look more like this, where this would be my zone, and this would be then a rise in temperature, and then I kind of come up here, and this is my zone, but it isn't actually a plateau. You can't see that, can you? Sorry. Let me try that again. So with an amorphous solid, all of the bonds are not equal in the solid. So some of them are closer, some of them are tighter, some of them are farther apart, some of them are looser. So because of that, it doesn't take the same amount of energy to break every bond. The easier bonds are going to break early on as it's adding heat, and the harder bonds are going to break later. But in the process, once I've started breaking some of these bonds, and I have a lot of them broken, I can start raising the temperature, but I still have other bonds to break. Because it is an amorphous solid, it's going to end up looking more like this. So I'm raising the temperature, but I'm also breaking bonds, but now I'm raising the temperature. So this might be my melting zone, but I'm also noticing on the increase. So I'm going to have a corresponding raise in temperature if I have a non-crystalline substance. And then the next one is, and I don't think I'm going to go any farther than this. I think I'm good with this because I don't want to do any more problems. The problems you have are enough, and we'll pick up with the rest of it on Friday. I know this has been a little bit longer, but I needed to do that because this is a block schedule today. So your homework is just going to be 21 through 25. We're not doing anything with this, but you should know this graph. There will be a quiz for the face-to-face students with the graph. You will plan on seeing this graph again on the test, and you should be able to explain what is happening in each of the pieces of the graph. All right, let me know if you need anything, but I will see you again then on Friday.